Dear friends and colleagues, I'm very pleased to welcome you all to our seminar on mathematical logic and category theorem. And today we're honored to have Graham Priest, distinguished professor at the Graduate Center of the City University of New York, speaking on the topic the mathematical infinite as an illusion. So, Professor Priest, thank you very much for accepting our invitation to speak at this seminar, and we're ready to start.
Okay, thank you, Ramazan. And first of all, thank you for inviting me to talk. Um, it's always a pleasure to meet with logicians, philosophers from other countries. I was just saying that the last time I was at the uh, HSE was before COVID, so it was a long time ago. But it was a conference on logic. I forget exactly what now, but it was a very enjoyable conference. Um, it would have been better to be with you in person today, but this is not always possible. So being with you virtually is the next best thing. So again, thank you very much for inviting me to your group. Um, let me explain what I want to talk about. Um, it's about mathematical finitism. Now, um, I know this is not a major interest for many philosophers or logicians, and not for me either. Um, I wrote this paper because in New York, Justin Clark Dunn at Columbia had a conference on mathematical finitism last year, the year before, which I wasn't actually able to get to because of other commitments. But he asked me if I'd write a paper for the proceedings. And so this is essentially, well, this presentation is based on the paper. And what I want to do is present a view to you concerning mathematical reality. Finitism is often about mathematics, but sometimes it's about physical reality as well. And I want to just make it clear that my concern today is only mathematical reality. The finitude of the physical cosmos is another question which I'm not going to talk about today. But the view that I'm going to explain to you is about mathematical reality. And according to this, there's only a finite number of things. So obviously, that's a very unorthodox view about mathematics. Um, Let me move that. Okay. But even though there's only a finite number of things, um, that there is an infinite number of things is an illusion. Now, what I mean by that won't be clear at the moment, but I will make this clearer as we go along. So the mathematical universe is actually finite, but that it's infinite is in a certain sense an illusion. And moreover, it's an illusion of which paradox is an integral aspect. So the illusion that the mathematical universe is infinite is deeply connected with paradox, very familiar paradoxes, in fact, as we'll see in due course. Okay, let me also say that I find this view interesting, but I don't think it's true. So I'm not going to defend finitism. I'm just going to present a view to you. Um, and I'm not even going to defend this as the best view of mathematical finitism. Uh, that would require a much longer discussion of many topics. But I do think that if you're a mathematical finitist, which I'm not. The view I shall describe of mathematical finitism is a kind of intriguing one and one that's worthy of consideration. So what I'm going to do today is not argue for a view, it's just to put a view of mathematical finitism on the table, as the English say. Um, and I'll be interested to hear your views, whether you think it's a crazy view of finitism or not. You might well do. We'll see. Okay. So the view I'm going to present of mathematical finitism uses some model theory, and it uses the model theory of paraconsistent logic. Some of you will be familiar with paraconsistent logics. Some of you, I can't assume that you all are. Um, Paraconsistent logics are logics in which the principle of explosion is not valid. So the principle of explosion says that contradictions imply everything. And of course, that's a view of inference that's endorsed by a number of different logics, including so-called classical logic, intuitionistic logic. But paraconsistent logics, which by definition are logics where that principle fails, are a well-established part of modern non-classical logic investigations. They were investigated first in the 1950s, 1960s, and now we know that there are many uh, paraconsistent logics which work on very different principles. Um, and I want to talk about one of them. And as I said, I'm not going to assume that you're familiar with this area. So in the first part of the talk, I will explain to you briefly the paraconsistent logic that I'm going to be dealing with. It's called LP, and one theorem in its meta theory, in its model theory, called the collapsing lemma. So the first part of the talk will be familiar perhaps to some of you, but I need to go over these technical preliminaries just to explain the use I'm going to make of them. Okay, so that's the first part of the talk. Then we'll get round to the heart of the talk, which is arithmetical finitude. And this spins off an application of the collapsing lemma, which produces finite models of arithmetic. So I'll talk about that, and then I'll talk about the connection between that and the paradox of illusion, or the illusion of infinitude, and the connection between that and paradoxes. Okay, so that's an application to arithmetic, but of course there's a lot more to mathematics than arithmetic. And there's set theory, which has a lot bigger infinities than arithmetic. Uh, so in the final part of the talk, I'll explain how the techniques that I've been talking about can be applied not just to arithmetic, but also to set theory, which for present purposes we can take as all of mathematics. I don't think it is, but that it is a fairly standard view. So that's where we're going. First of all, some technical preliminaries, then the discussion of arithmetic finitude, and then an expansion of a discussion to set theoretic infinities. Okay, that's where we're going. So let's start with the technical preliminaries. And these concern one particular paraconsistent logic. As I've said, there are many well-known now paraconsistent logics, but this is perhaps the simplest, or at least one of the simplest. And if you understand classical logic, it's not hard to understand this logic, because this logic, which goes by the name LP, is essentially classical logic with one difference. The one difference is that the extensions and anti-extensions of predicates can overlap. And a consequence of this is that in an interpretation, truth in interpretation and falsity in interpretation can overlap. Apart from that, this is exactly the same as classical logic. Okay, so let me spell out the details. Um, and I'm going to give you a semantics of LP. The proof theory is well understood, but I'm not going to be talking about that today. So, first of all, the language. The language is the standard language of classical first order logic. Um, Let me see if I can move this. All right. Um, so the language is the one that you are familiar with from first order logic. And I'm going to take negation, conjunction, and the universal quantifier as primitive. And the other connectives and quantifiers can be defined as usual. So in particular, the conditional, the material conditional, is defined in the usual way, so that A hook B is defined as not A or B. So all perfectly standard. Okay. Now, what does an interpretation of this language look like for this logic? Well, it's going to look very familiar to you. It's a structure which has two components, a domain of quantification, D, and a denotation function, which I'll write as delta. So D is a non-empty set of objects, and the denotation function, delta, functions in a very standard way. Namely, for every constant C, delta of C is a member of the domain. It's the denotation of the constant. For every n-place function f, its denotation is a map from d to the n to d. All very standard so far. And for every n-place predicate, its denotation is a set of pairs xy such that the union of xy is d to the n, set of all n-tuples in D. Okay. Now, this is where it differs from classical logic. Sorry, I'm trying to make the whole of the slide visible at the same time as at least seeing some people. Okay, let's see if that's any better. So every predicate has a denotation, which is a set of pairs of n-tuples. And I'm going to write x as delta plus p and y as delta minus p. And delta plus p is the extension of p. So it's a set of things or n-tuples that make p true. And delta minus p is the anti-extension. So that's the set of things which make the predicate false. Okay. Of course, in classical logic, you don't, if you know the extension, you don't need to mention the extension, anti-extension, because it's just the complement. But as I've said, in this logic, the extension and the anti-extension for a predicate can overlap. They kind of union up to the whole domain. You can get rid of that condition, but today it's in place. But the important thing is that the extension and the anti-extension of a predicate may overlap. The language has identity in it, as I said, and the extension of the identity predicate is going to be just the usual thing. It's a set of all those pairs of objects in the domain such that the first is the second. And if that is the extension of the identity predicate, identity works in exactly the way you're familiar with. Um, Oddly enough, the anti-extension of the identity predicate plays very little role in logic. It's the extension that's doing all the work. So if you insist that the extension of the identity predicate is what you're familiar with, then identity is going to behave in a very standard way. Okay, so those are the components of an interpretation. All right, what do you need next? Well, you know um, what the components for interpretation are. Next, you need the denotation conditions and the truth and falsity conditions. So the denotation conditions are on the screen. They're standard, not much to be said about those. Um, because truth and falsity are not exclusive, you now need to give both truth and falsity conditions. Of course, in classical logic, if you know one, you know the other because they're kind of the complement. But now we need to give truth and falsity conditions. And for atomic sentences, P of T1 through Tn, that's going to be true. That's what this little plus means by this turnstile. P of T1 through Tn is true just if the interval of the denotations of the T's are in the extension of P, and sort of dually for the anti-extension. So the plus means true, the minus means false. So those are atomic sentences. For the connectives, well, they work exactly as they do in classical logic. Not A is true if A is false, and not A is false if A is true. For conjunction, conjunction works in the way you expect. A conjunction is true if both conjuncts are true, and false if at least one conjunct is false. What about the quantifiers? Well, there are different ways of doing the semantics of quantifiers, as I'm sure most of you know. Um, you can do this in terms of satisfaction if you want. Uh, Over the years, I've found that the easiest way to get people's head around quantifiers is simply to assume that every object in the domain has a name. So I'm going to do it that way. So I'm going to assume that the language is augmented with a constant little c of d, such that the denotation of c of d is just d for every d in the domain. And now it's easy to give the truth and falsity conditions of a universally quantified sentence. For all xa is true, just if for every d in the domain, when you substitute the constant denoting d for x in the formula A, which is what this thing means, the result is true. And a universally quantified sentence is false if some substitution instance is false. So these are the classical truth conditions. Okay, and as I said, you can define the other quantifiers, the other connectors in the usual fashion. Okay, you know what an interpretation is, you know what the truth and falsity conditions are. The final thing you need, of course, is the definition of logical consequence, and that's standard. Let me just read it. So that if you've got a set of sentences, and we're just dealing with closed sentences here, you've got a set of sentences, premises sigma, and a conclusion A, then A follows from sigma just if for every interpretation, if every premise, every member of sigma is true, so is A. So it's very familiar. It's the definition of truth, definition of validity in terms of preservation of truth in interpretation. Okay, so that's the paraconsistent logic LP. And as I said, it will look very, very familiar to you because it's essentially classical logic where you get rid of the assumption that truth and falsity are exclusive and exhaustive. In this particular logic, truth and falsity are exhaustive, but they're not exclusive. But notice that there's no requirement that every interpretation is such that truth and falsity in that interpretation overlap. There can be perfectly good interpretations where they don't overlap. And if they don't overlap, then you've just got an interpretation of classical logic. So every classical interpretation is an LP interpretation, but not vice versa. So what that tells you is that LP is going to be a sublogic of classical logic. And in particular, explosion is not valid. Uh, it's pretty easy to construct a counter model to explosion in these semantics. I'll leave that as an exercise for those who are interested. All right. So that's the logic LP. And apologies if that's familiar to some of you, but I couldn't assume that everyone will know this. So I did need to spell this out. All right. So we're still on technical preliminaries here. What I want to do next is to give you one theorem from the model theory of LP, and it's called the collapsing lemma. And it will be clear why it's called that when I've explained the lemma to you. So the collapsing lemma works as follows. Let A, fractor A, be any LP interpretation. And as I just said, every classical interpretation is also an LP interpretation. So A could be a classical interpretation. Now let tilde be an equivalence relation on the domain. In fact, we need a little bit more than that because I don't want not just an equivalence relation, but tilde must also be a congruence relation on the denotations of the function symbols in the language. So just take a monadic predicate. If T and S are terms whose denotations are in the same equivalence class, then if you apply function symbol to that, that's also in the same equivalence class. That's for a monadic predicate, but it works for the same thing. So a congruence relation is exactly what you're familiar with in model theory. So tilde is an equivalence relation on the domain, which is also a congruence relation on the function symbols or the denotations of the function symbols. All right, bit of notation. If D is in the domain, I'm going to write D in square brackets as the equivalence class of little d under the equivalence relation. Again, that's pretty standard notation. All right. Now, I'm going to use the equivalence relation to define a collapsed interpretation. Now, I'll give you the definition of this first, and then I'll just say a little bit about it. So the collapsed interpretation, I'm going to write as A tilde with these components. And the domain of the collapsed interpretation is the set of equivalence classes of the objects in the domain of our original interpretation. Okay. What about the denotation function? Well, for every constant in the language, its denotation is going to be the equivalence class of the denotation in the original interpretation. So delta tilde C is just the equivalence class of delta C. For function symbols, for every n-place function symbol, f, the denotation of f in the collapse interpretation is just what you'd expect it to be. And here I'm using the fact that it's a congruence relation. This definition does not make sense otherwise. But given that it's interpretation, given that it's a congruence relation, you just do the obvious thing. And then you need to know what the interpretations of the predicates are. And let's just talk about the extension. The anti-extension is the dual. So if D1 through Dn are in the domain of the collapsed interpretation, those are in the extension of P, just if some member of D1 through Dn was in the extension of P in the uncollapsed interpretation. So what's going on here? Well, what the equivalence relation does in effect is partition our original domain into a bunch of equivalence classes. The equivalence classes are going to be the objects in the domain of the collapsed interpretation. And let's just think of a monadic predicate for a moment, just to keep it simple. When is an equivalence class going to satisfy a monadic predicate in the collapsed interpretation? Well, it's just going to be when some member does. So obviously, we're creating some new objects, and the new objects are kind of amalgams of everything in an equivalence class. So the equivalence class is going to have the property of any one of its members. So we're sort of mushing them all together uh, to produce a bunch of compound objects or um, collapsed objects, if you like, which have the properties of each of their members. Okay, that's what this construction is doing. And so you can see now why it's called the collapsing lemma. Although I haven't told you what the collapsing lemma is, let me tell you what it is. First of all, it's not difficult to prove the following. I'm not going to give you the proof, it's in the literature. For every closed term, the denotation of the term in the collapse interpretation is just the equivalence class of the denotation of the term in the uncollapsed model. And then, having proved that, you can prove the following. This is the collapsing lemma itself. If in our original interpretation A is true, then in the collapsed interpretation, it's still true. And if in the original interpretation A is false, then it's still false. Now, because of the collapse, lots of new things are going to be true and false. You're going to pretty obviously, even if you start off with a consistent interpretation, a classical interpretation, then what you get won't be a classical interpretation, because you've produced these new compound objects which are going to have inconsistent properties because their members are going to have inconsistent properties. So you've produced a new interpretation, which is going to have more truths and more falsehoods, but at least all the old truths and the old falsehoods are going to be preserved. Okay, that's the collapsing lemma. Um, so let me say it again. The collapsed interpretation is going to preserve all the truths and falsities in the original uncollapsed interpretation, plus some others. All right. Now, that's taken a while, but I didn't want to rush through it because what I want now to do is um, apply the collapsing lemma in a certain way. Okay, but the details may not have been familiar to many of you. So what I'm going to do is pause there for a second to see if anyone wants to ask any clarificatory questions before we go on to applying this machinery that I've described. And Ramazan, I can't see the audience, but you can, I presume. So can you just see if anyone wants to ask a question?
Okay. Right now there is no question at the chat, so we can go now.
Okay, all right. So hopefully what I've said will be clear, um, even if you haven't met this kind of logic before. Um, all right. Now, let us apply this to arithmetic finitude. Okay. So what I'm going to do is take a model of arithmetic, and it can be the standard model, and collapse it. All right. So there are many ways of doing this. Um, what collapse does, in fact, give you is a whole family of non-standard models of arithmetic. And you'll probably know that there's a study of non-standard models of ordinary arithmetic. All those are collapse models in a certain sense. Um, but what you've got is a whole richer structure of non-standard models of arithmetic. Um, and this, this, the structure of this class is actually quite well known now. But I'm not going to talk about that because it's just one particular application, which one particular kind of non-standard model, which is going to interest me. Okay, so let's produce a collapse. So take the usual language of first order arithmetic. It's what you're familiar with, no funny business. In particular, maybe I should say that there's one constant symbol, zero, and then function symbols for successor, addition, and multiplication. Okay, now let n be the standard model. Um, let its domain be Roman n, and if n is a member of the standard model, let its numeral be boldface n. Okay, that's fairly standard notation, but it's pretty obvious anyway. All right. Now, um, there are many ways of collapsing the standard model. Lots of them they're not all finite. Some of them are rather interesting, but I'm not going to talk about the general structure today. I'm going to collapse this into a finite model. Okay, so choose some number. Let's call it m. And I've chosen m because m is for max. So it's going to turn out to be, in a certain sense, the maximum number. Okay. And now define an equivalence relation as follows. I tilde j, just if I and j are less than m and I is j, or I and j are greater than or equal to m. Now, what this is doing, if you think about it for a moment, is this. It's going to leave all the things less than m alone. We're not going to fiddle with those at all. But what it's going to do is collapse all the things greater than or equal to m down to each other. So all those things which are greater than or equal to m are going to be in one single equivalence class. It's going to be big, okay? So the collapsed domain is going to have essentially a singleton of every number less than m, and then just an equivalence class containing everything greater than or equal to M. All right. Um, uh, you can show that's not just an equivalence relation, that's a congruence relation. This results in the literature. I'm not going to hammer through the details. You can take my word for it. All right. Um, so I'm going to collapse with this congruence relation, and I'm going to call the collapse model M, just otherwise the notation gets a bit messy. All right. So let T be the set of sentences true in M. Then for any A, either A is in T or not A is in T, though maybe both are. So in other words, the set of sentences true in the collapse model is complete. Um, it contains every sentence or its negation. In fact, it contains everything true in the standard model because we know by the collapsing lemma that when you collapse, it preserves all the truths. So in the collapse model, everything true in the standard model is true. And of course, everything false in the standard model is also false. But there's going to be more stuff as well. Um, okay. Um, so what does the model look like? Well, here's a little picture of it. The arrow here indicates the successor relation. All right. Um, and the the model has a kind of consistent tail. The equivalence class of 0, the equivalence class of 1, up to the equivalence class of m minus 1. Each of those behave as you'd expect. Each is a successor of the other. And then you've got this hyper big equivalence class, which are all the other things. So M and everything bigger in it is in this equivalence class, and that is its own successor because it contains every object um, bigger, greater than or equal to M plus its successor. Okay, so as I said, we've collapsed down everything greater than or equal to M into a single object. All right. So for natural numbers, I and j, um, there are some very simple facts that you can check. Namely, every instance of identity is in T. It's true in the collapse model. I'm not going to hammer through the proofs of these. They're straightforward. You can take my word for it. Um, and if I is less than M and I is not equal to J, then the statement I is distinct from J is also in T because, hey, it was true in the uncollapsed model, so that's going to be preserved. However, if I and J are greater than M, then what's true in the collapse model is that I is J and I is distinct from J because that's the way that the identity predicate works in the collapse model because we've identified all the things greater than or equal to J. So their numerals are going to be such that if I and j are numerals, then I is equal to j and I is not equal to j, and those are both going to be true in the collapse model. Okay, but clearly M is finite. Moreover, M verifies all the truths in the standard model. That's just an application of the collapsing lemma. Um, and moreover, since M is finite, it's decidable. Okay, that's just standard model theory because um, The basic predicates are decidable, and because the model's finite, then quantifiers are going to work like finite disjunctions or conjunctions. So M is finite, so T is decidable, and since it's decidable, it's axiomatizable. Now, of course, it contains as a subset all the things true in the standard model, so it has subsets which are not axiomatizable, but of course, decidable and axiomatizable sets can have subsets which are not decidable, not axiomatizable. That's just standard recursion theory. All right. So that's a simple application of the collapsing lemma. Now you can see where we're going with this, hopefully, because uh, let me explain the kind of obvious application of this to arithmetic finitude. So I'm going to explain to you a view according to which arithmetic is finite. All right, how does it go? Well, M, the collapse model, is what the arithmetic world is really like. So true arithmetic, if you're this kind of finitist, is given to you by the collapse model, M. Now, the standard objection or a standard objection to mathematical finitism is that it doesn't give you as much arithmetic as you want because you've only got a finite number of numbers to play with, right? Now, what you've just seen is that the collapse model provides you all the mathematical truth you could possibly want because it verifies everything in the standard model and more, of course. Um, so this version of finitism overcomes the biggest objection to mathematical finitism, is which is just that there's not enough arithmetic to go around, as it were. Okay, of course, it gives you the collapse model gives you uh, all the truths you could possibly want, but it is going to give you more. And of course, it's going to give you some contradictions too, as I've already noted. Um, you might object to dilethism, the view that some contradictions are true. Um, if you do, you're not going to like this model. Um, but if you object to dilethism, it's got to be for much more general principled reasons. Um, and you might want to object like that. I'm not going to discuss that now because a lot of literature has been discussing that in the last 30 or 40 years. So I'm just going to assume that inconsistency is not per se an objection. We can argue about that if you want. So the main point is that um, this collapse model gives you all the arithmetic you want and some more, but then such is life. Um, Moreover, and importantly, it explains why we're inclined to the view that finitism is false. Remember, I told you that I was going to tell you that although the mathematical world is the arithmetical world is finite, uh, there is an illusion of infinitude. Why so? Well, M is finite. Okay. So, mathematical, we're assuming that that gives you math or arithmetical reality, and that's finite. However, Since M verifies all of standard arithmetic, it verifies claims which appear to say that there's an infinitude of objects. So, for example, this is true in the standard model, and it just says for any object you like, um, there's something which is greater than all the things less than it, which is one way you can express the infinitude of the natural numbers. Um, okay, so the model is actually going to tell you things which appear to say that the arithmetical world is infinite, even though it isn't. So that is why I say that the model itself gives mathematical infinitude the illusion of truth, because the model appears to verify things which say that arithmetical structure is infinite, but it's not. It's just an illusion. So here's an analogy. Listening to what the model says is like listening to someone who's self-deceived. So the model is finite, but it says, hey, there's an infinite number of things. Okay, which is actually not the way that the mathematical reality is. So, as I say, listening to what the model says is a bit like listening to someone who is self-deceived. All right. Okay, so that's the basis of the view of mathematical finitude that I want to give you, um, and why, if that view of mathematical finitude is right, there is an illusion of infinitude, which kind of explains why we're inclined to the view that arithmetic is infinite, though it's not. All right. So we haven't quite finished with arithmetic yet, because what I promised you is that there's a connection between this and paradox. So I've already noted that this model is going to produce certain contradictions. In fact, some of those contradictions are ones which are very familiar to you in the shape of paradox. Let me explain. Okay. Um, Look, what I've told you is that the set of things true in M, the collapse model, is decidable. And since it's definable in the standard model by a formula in the language of arithmetic is one free variable. B, Beweis in German, if you like. Okay. Now, for any sentence A, closed sentence, if A is T, A is in T, then it's the statement that it's in T is true in the standard model because it's a decidable set. So to say that it's in that set is true in the standard model. And if it ain't in T, then its negation is true in the standard model. And here I'm just using A in angle brackets as the numeral of the Gödel code of A. All right. So we've seen that T is decidable. It's going to be definable in the standard model by B. So if it's in T, then in the standard model, BA is true in the standard model. Okay, but now by the collapsing lemma, if it's true in the standard model, it's true in the collapse model. So in the collapse model, if A is in T, then to say that it's in T is also in T. And if it's not in T, to say that it's not in T is also in T. So T has a certain kind of closure property, which is kind of interesting because it has various consequences. And here's one. By diagonalization, there's a formula G, which is of the form not BG. So G is for Gödel, of course, and this is the sort of undecidable sentence which says, hey, I'm not provable. Okay, I'm sliding over a subtlety here, um, which is that if you do this thing in standard first order arithmetic, uh, the formula G is not actually literally identical to BG, it's materially equivalent to it. Um, that doesn't make a real difference classically. It sort of does here. Um, and we can talk about this assumption more if you want to. But there are ways of setting up the thing in such that G is actually literally identical to not BG. So I'm just going to work with that because it simplifies some of the things I'm going to say. Okay, so there's a Gödel sentence G which says, hey, I'm not provable. All right, now either G is in T or it isn't. And if G is in T, then B of G is in T, but B of G is not G of T, so G and not G is in T. But if G is not in T, then its negation is in T because it's complete. And since not G is in T, or since G is not in T, not B of G is in T as well. So in either way, G and not G is in T. Now, G is the Gödel undecidable sentence. And of course, if the system were consistent, you'd be able to prove neither G nor not G. But in the collapse model, you can prove both it and its negation. So it's no longer undecidable. You can say that it's overdetermined rather than underdetermined, if you like. All right. Now, of course, the Gödel undecidable sentence is involved in some things which are very close to paradox. Um, Namely, there's something that's called, that I've called the Gödel paradox. Because if you reason naively about the sentence, this sentence is not provable, provable here is naive proof, it's not proof in a system. But reasoning about the sentence, this sentence is not provable, you can prove that it's both provable and not provable. This is kind of the Gödel paradox. And in a sense, it's behind the Gödel theorem, although, of course, it doesn't prove that, say, Peano arithmetic is inconsistent. But if you track through the argument as to why you can't reproduce the paradox in, say, Peano arithmetic, what you'll see is that there's a crucial step in it that doesn't work. It appeals to what you might call Loeb's principle, namely, if something's provable in, and in this case in T, or the collapse model, then if BA, then A. All right. And as you know, uh, you cannot prove the Loeb principle in Peano arithmetic. What you can prove only those instances such that A is already provable. This is Loeb's theorem. Now, what happens to the Loeb principle in the collapse model? Well, either take A, either A is in T or it isn't. In the first case, you've got Loeb because this is a material conditional. And in the second case, you've also got Loeb because if A isn't in T, then not BA is in T. So you've got Loeb, okay? Because it's a material conditional. Not only do you have Loeb, you have converse Loeb for very similar reasons. Either not A is in T or A is in T. And the first case gives you converse Loeb because this is the material conditional. And the second case also gives you converse Loeb because BA is in T by the result of the collapsing lemma. All right. So what we've just seen is that you've got lerb and converse lerb. So you've got this. And if that looks familiar, well, it is familiar. It's the material Tarski T-schema. So given that you've got the Tarski T-schema, what I called the Gödel paradox about this sentence is unprovable collapses into the the lie paradox. This sentence is not true. Okay. So what you've now seen is that the collapsed interpretation is really closely connected with some very familiar paradoxes, such as the liar paradox. So, okay, I've just said that. So let's go on. So what I've shown you is that arithmetical finitism is deeply embroiled in paradox. Okay. Um, so paradox is a necessary condition for the finite models. Um, it would be nice to say that the paradoxes don't arise in infinite collapse models, but actually they do. Um, some of the infinite collapse models are also axiomatizable. That's a result of Jeff Paris and one of his co-workers. But nonetheless, paradox is a necessary condition for the finite model. Um, and so the illusion of infinity, which I've already explained, presupposes paradox. So there is a very close connection between this version of mathematical finitism and some very familiar paradoxes. And as was clear from the start, the collapse model is going to verify inconsistent things. And that might seem rather strange. However, the fact that some of these are very standard paradoxes might make the inconsistency of the collapse model a bit more homely, as it were. Okay, so that's the second part of the talk. I've now been talking for an hour. Um, there is a third part of the talk, which is about set theory, um, where what I will show you if I do that is that the same phenomenon applies to set theory. But we've covered sort of the guts of the talk now, so I'm not sure whether I should go on and do the third part of the talk or rather give you a chance to answer questions. So Ramazan, what do people want me to do? I'm aware that I've been talking for an hour and I'm talking a language which is a non-native language for most of you.
So I think it's okay, and we can continue with it.
Okay. So
So
if I do this, it's going to take another 20 minutes. Is that okay? Okay.
yeah, okay.
All right. So look, uh, a natural reaction at this point is, yeah, okay, you've told us about arithmetic, but arithmetic's kind of special. Um, and there's a lot more to mathematics than arithmetic, of course there is. Uh, and once you move to the bigger picture, and let's assume the big picture is ZF, uh, I actually don't think that ZF has contains all mathematics, but at least this sort of reductionist assumption is that you can do all mathematics in ZF, so let's just work with that. Okay, once you move to Zamilo-Frankel set theory, you're going to have a lot more infinities, a lot more bigger infinities than you get in arithmetic. Of course you are. Um, and you might want to say, well, okay, you've given us a story about finitism, which works for arithmetic, but what about the rest of mathematics? Okay, What I'm going to show you now is that it works for the rest of mathematics, or at least for ZF. Okay, so um, that's the objection. What I've said so far deals only with arithmetic infinities, not all the others. Um, and what I'm going to show you is that the techniques that I've given you about collapsing can be applied not just to models of arithmetic, but models of set theory too. Okay. In fact, when you're dealing with models of set theory, things get quite a lot simpler because if you formulate ZF in the usual way, there's just one predicate to worry about, namely set membership, which I'll write like this. Identity can be defined in this way. So the identity axiom just becomes that if X is Y, then anything that X is a member of, Y is a member of. And moreover, there are no constants or function symbols to worry about. So you don't have to worry about uh, the thing being a congruence relation. All right, so take any model of ZF, working within it, and let me emphasize that I'm now working within a model of ZF. We'll come back to relaxing that in a minute, but let's just work in the model of ZF. So working within the model of ZF, let B be the cumulative, let V be the cumulative hierarchy with levels V alpha for every ordinal alpha. Okay, I'm going to collapse it. So let M be any finite ordinal. So M is again for max. It's a finite ordinal, but it's kind of the maximum finite ordinal. And here is an equivalence relation. X tilde Y, just if X and Y are in VM and X is Y, or they're not in VM. So what we're doing is essentially what we've done in arithmetic. We're leaving the things in VM alone. And we're going to collapse everything else down to one single equivalence class. It's going to be big, but that's okay. Call the collapse model fractus C for collapse. All right. Now, let's think about this really large equivalence class. Let me call it omega. There's nothing, I mean, I'm not choosing that name for any particular reason. It's just a convenient name. So omega is going to be the equivalence class of all the things which are not in VM. So the domain of the collapsed interpretation is just all the singletons of things which are in VM plus this really big equivalence class omega. Okay, but now you can see much the same is true of this as was true of the collapsed model arithmetic. C is finite. Okay, there it is. It's also a model of ZF because that's the content of the collapsing lemma. So we've got a finite model of ZF. And so exactly the same considerations apply to this as applied to arithmetic. Let's just think for a little bit about the membership relation in the collapse model. So let's write that as epsilon with a subscript fractus C. Now, if X and Y are singletons, then any statement of that X is Y is consistent because we haven't fiddled around with the consistent part, the things in VM. All right. But it's not the case that omega is in X, one of the singletons, and that's going to be consistent. But if X is one of these singletons, X is in omega and not in omega, because omega is going to behave really inconsistently. And also, omega is in omega and not in omega, because omega behaves really inconsistently. All right. Again, I'm not going to hammer through the details of the proof. They're very simple. You can take my word for it. Okay. But as with arithmetic, um, the set theoretic reality is actually finite. But again, it verifies statements saying that there are very large infinities. For example, I don't care how you express this, but there are going to be sets with arbitrarily large infinitudes, because you can express that in the language of a set theory in ZF. Um, and the collapse model is going to verify those by the collapsing lemma. Moreover, this illusion of infinity is embroiled in paradox just as much as the arithmetic analog. Okay, because since arithmetic is interpretable in set theory and C is finite, the arguments concerning Gödel's paradox and the Liar paradox apply just as much to it. So we could just run the arguments about Gödel's paradox and the Liar paradox as before. Not only that, we've now got not only those paradoxes, but we've got, guess what? The set theoretic paradoxes. So in C, you can prove that there is uh, there is not a set that everything is remembered. There's no universal set because that's true in ZF, right? Provable in ZF. But now there is a set such that everything is a member of it, namely omega. So what is this? Well, it's Cantor's paradox. Um, I'll consider the Russell set. Okay, you know what that looks like. Um, how does that behave in the collapse model? Well, that set contains every set. And so this is just omega. So in the collapse model, omega is in omega and omega is not in omega. We've seen that. So this is Russell's paradox. Okay. So I told you these collapse models are deeply embroiled in paradox. And when you collapse a model of ZF, you get not only the arithmetic paradoxes, but the set theoretic paradoxes too. Okay. All right. Now, there's one more thing that I need to talk about because some of you will be thinking quite correctly, look, hey, priest, you've been talking about collapsing models of the universe, but you haven't collapsed the universe itself. You've only collapsed models of it. In fact, all the proofs you've done are in ZF. And so you're presupposing the universe of sets, because that's what ZF talks about. And so you haven't really got rid of these infinities by collapsing models of set theory. You know you can do strange things with models of set theory. You've still got the whole bloody universe itself. And that's a fair point, even though I can't spell universe. Okay. Um, Now, the last thing I want to show you is something you might not expect, even given what's come before. I'm going to show you you can collapse the whole universe. Okay, let me show you that. So we're going to do it essentially the same way, but if you try and do it in the natural way, you hit a problem, and that problem needs to be got around. So let me show you how you would do it in the straightforward way, point out the problem to you, and then tell me how you get around the problem. And I'll tell you then how you get around the problem. Okay. So that's the last part of this talk. Um, okay, now let's work within ZF itself, not within models of ZF, but within ZF itself. Let's define this equivalence relation. It is an equivalence relation um, where M is a finite ordinal. Okay. So obviously that's an equivalence relation. Let's collapse, or let's try to collapse with that equivalence relation and see what happens. So suppose we do the collapse construction. Um, let's write the collapse construction as D for the domain, and then we need an interpretation for the membership predicate. It's going to have an extension and anti-extension. Let's write it like this. It just simplifies notation a bit. All right. Suppose we collapse with that equivalence relation, then what do you get? Well, first of all, the domain is the set of all equivalence classes. So for every A in V, there's going to be the equivalence class under this equivalence relation. That's the domain. And secondly, um, how do you define the positive and negative extension? The extension, anti-extension, or epsilon, well, you do it this way. Okay, and that's just the same as before. All right. So that would be the flat-footed way of doing it. And now something has gone wrong. What's gone wrong? Well, look, come back to this domain. Um, come back to the equivalence class of all the things which are not in VM. That's proper class size. So its equivalence class is going to be a proper class. Okay, so it cannot be a member of D because proper classes can't be members or anything. Okay, so what I've shown you is the kind of most straightforward way of collapsing the universe, and it doesn't work because you hit the problem that one of the things you're dealing with is a proper class, and it just screws up the construction. All right, that's the problem. Now I'm going to tell you how to get around the problem. Okay, and it's very straightforward actually. Um, if you're used to working with kind of equivalence classes, um, you'll know that when you do that, um, a very standard technique to keep things sort of small is to choose not the whole, or to work with not the whole equivalence class, but just one of its members, a typical member. That's exactly what we're going to do here. So instead of working with the equivalence classes, we're going to work with one of their members. And then if you do that, then you avoid the problem of having to work with a proper class. Okay, so let theta D be a member of D. Okay, now that looks like the axiom of choice. In fact, it looks like the global axiom of choice, but in fact, it is not because we're only going to apply it to a finite number of objects. And so, since we're only doing a finite amount of choosing, this is not the axiom of choice. So we've chosen a member of each equivalence class, but in fact, we're not really using the axiom of choice because there's only a finite amount of choosing going on. All right, now let's define the domain not as D, but as D down. And D down is just a member of each of the equivalence classes that we had before. And there's only a finite number of these, so we've still got a finite model. Okay. Um, so now we define the collapse model as D down, and we've got to define the membership relation. Um, we had to change that slightly because the old definition won't work. But you do the obvious thing, and you define it as follows. So D1 and D2 are going to be in the extension of epsilon, just if you can't say uh, you can't just talk about D1 and D2 themselves. You've got to talk about something which is equivalent to theta of D1 or theta of D2. And if you do that, then you get this definition. All right. So again, this is a standard construction of just defining a function, a structure on equivalence classes by choosing a particular member of each class. Okay, now what you can show is that if A is true, then A is true in the collapse model. And if A is false in the collapse model. Again, I'm not going to hammer through the proof, but the proof, all these proofs are by a simple induction on the grammatical formation of A. And the argument is essentially the same. Okay. And again, you can take my word for that. It's true. Um, but what this version of the collapsing lemma shows you is that you can collapse the whole universe. All right, you're still proving that in ZF. But hey, the collapse model is a model of ZF. So you can think of the proof as proving something within ZF. Okay. So it's not only have you got a finite model, but you've got a finite model in which you can actually prove what you want to prove, namely that the finite model is a model of ZF. Okay. I think maybe that's the most surprising thing of this talk, but there you go. All right. So that's the end of the talk. So let me just summarize what I've said. Um, oh, that's the end. Okay. So let me summarize it. So what I've shown you is that assuming that you're allowed to use the tools of paraconsistent logic, um, you can take arithmetic or set theory and you can collapse it into a finite structure. The finite structure, even though it's finite, verifies everything that's true in the standard model of arithmetic or everything that's true in ZF. Um, so if you take that structure to be what mathematical reality is really like, then finitism is true. But it gives you as much mathematics as you want because the structure verifies everything in the standard model or everything in ZF. Okay, there's a price to pay, which of course is inconsistency, but you've already seen that the inconsistency, or at least some of it, is very familiar to you. It's some very familiar paradoxes of both arithmetic and set theory. Okay, so as I said right at the start, I'm not endorsing mathematical finitism. I'm not endorsing this account of it. But I do find this an intriguing account of mathematical finitism, and I'm curious to know what you guys think of this. Okay, so thank you very much. I'm sorry I've talked for quite a long time. I hope I haven't outstayed my welcome. So let me stop sharing my screen and then we can see what you guys want to say.
So, dear professor, thank you very much for your talk. It was really pretty nice. So, we're ready to answer two questions and answers. So, the question with a raised hand from Arsene. Arsene, you board? Yep.
Can you hear me?
I
Yeah,
can.
I hear
Go
you.
ahead.
Thank you for your talk, but could you go back to the slide with the model construction?
Okay, so you want me to put the slides back up, right?
Yes.
Okay, so yes, okay. So we want to go right back to the start, okay?
Here, collapsing models.
Um, well, that's models of set theory.
N-
I mean,
No,
it's not,
no.
I want to do arithmetic.
Uh, 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 no. Go to the end of the talk with constructing collapsing models of ZF.
Okay,
Mm.
so that's the actual construction.
Uh, Further,
That's the collapsing lemma.
further. Uh,
All the rules.
uh, when you talk about cumulative hierarchies,
Hmm.
this slide.
Um, that one here.
One slide back. Um,
I just the collapse of a model. Okay, that this
one
one.
slide, but this one.
Okay.
I think that when you write a definition of equivalence, I can go wrong, but in model theoretic terms, this equivalence relation is not congruence for the atomic formula like x in y, because the truth of membership depends on the choosing representatives.
Okay, slowly. Um, I required a congruence relation when you've got function symbols. There are no function symbols in this language.
But what about that the equivalence relation is not compatible with membership? So the
I'm,
question structure
I'm not
by this equivalence
convinced.
is not even well defined in the language of relation
Okay,
x
I
in
don't.
y.
So you're telling me this bullet point is not well defined? Why is
Yes.
that?
No, uh, you can take any finite m in the given relation. All sets outside VM are identified into one class, call it omega. You can choose a VM, B singleton of VM, C singleton of VM. All three are outside VM, hence a equivalent to B, B equivalent to C, so A equivalent to C. So in the quotient, they all become the same element omega, but in the original model, A in B while C not in B. Therefore, if you construct the equivalence classes, X in Y is supposed to mean X in Y, but in the square brackets. Then the truth of the membership depends on the chosen representatives. Therefore, it is not congruence. Maybe I am wrong, but
Well, I'm at a bit of a loss because I don't need congruence. I mean, all I need is that this is an equivalence relation. So it's reflexive, symmetric, and transitive. And I'm failing to see why this is not reflexive, symmetric, and transitive.
but hence you cannot form a quotient model this way. No,
Why
because
not? It's an equivalence relation. If it's an equivalence relation, I can define equivalence classes.
I think that the truth of membership in this way depends on the chosen representatives. That incorrect definition of the equivalence relation.
But look, this definition doesn't use chosen representatives. I did when I collapsed the cosmos, the whole universe, but this is from the just collapsing a model.
Okay, thank you. I
Okay,
got the answer.
maybe there's some problem here that I don't understand. That's always possible. But yeah, look, I really don't see what's worrying you.
Maybe I will try to email you soon.
Okay, that's
Not
good.
now.
Yeah, please do.
So the next question from Stanislav in the chat. Does finiteness lead to the conclusion like any development has a boundary, limited or constrained, or development taking place on circularity, what we do with plurality?
Okay, I'm not sure that I've grasped the question. Can you read it to me again slowly, please?
You can see this question in the chat.
Oh, how do I find the chat? Let's have a look. Chat. Okay.
From Stanislav.
Okay, so it's from Stazov, right? Does finiteness lead to the conclusion any development has a boundary, limited or constrained? What's a development?
I am badly speaking on English, but I
Okay,
can say
your English is much
development.
better than my Russian.
Да. Yes. Development, I mean science development, development philosophy, development. No, how can I explain you development? No, but
Okay.
развитие,
The
on
progress.
Russian развитие, любое science development.
He means science progress.
Progress, maybe progress.
Oh,
Any
well,
progress has a boundary, unlimited. After we can conclude that or any has a limited, so progress is not possible.
okay. Look, first of all, I refrain from talking about science. Okay, I'm just talking about mathematics.
Only mathematics.
Yes. I mean, I actually don't think that this will give you enough mathematics to do science. But I didn't talk about that because there was already too much to talk about. But I mean, you might ask your question about mathematics. Does it prevent progress in mathematics? And okay, we might argue about what constitutes progress in mathematics, but I don't see that anything I've said endangers a view of progress in mathematics.
Mathematics is part of science.
Yeah, okay.
Important part of science. Mathematics influence on progress any area of sciences. How is achieve consistent if we make a conclusion is mathematics is finite.
Well, look, again, let me emphasize that I wasn't talking about empirical science. That's a much harder question, and I don't really think that you can do justice to empirical science with the mathematics that I've described today. Um, but I mean, I've just described to you a bit of mathematics. Now, I mean, mathematics, as far as science goes, mathematics is is a toolbox. Empirical scientists will use whatever bits of mathematics work for them. And I haven't taken away any tools that you thought you had already. I've just given you some new ones. I'm, but I'm not sure that really addresses your problem.
Thanks. Mm, for me, it is unclear. I think mathematics is very important part of science.
I agree with that. I agree with that.
It give quantitatively mathematics helps us to make theoretical models.
Correct.
We can develop, we can compare experimental results with calculation results. We can compare, we make what is true, what is false.
Okay.
Our conclusions, we propose proposement. So I finiteness of some part of mathematics maybe is possible, but
it's finite model, not arithmetic.
Okay, look, what's true in the collapse model is true. Let's just talk about arithmetic, okay? What's true in the collapse model is everything that's true in the standard model. So you've got everything you could possibly want for in terms of arithmetic. That's not a problem, okay? What is a problem is that you've got more than that. You've got some inconsistencies to deal with too. Now, I personally think that if you try to use those inconsistencies in empirical science, you're going to run into trouble.
what I want to say, maybe finiteness is connected with himself, with limited of possibilities of humankind, human thinking, for our thought, our thinking. But nature, and is every science is infinite. So we put a boundaries between our possibilities, human possibilities, and nature existence.
Well, that may be true. I mean, I'm not exactly sure how to apply those thoughts to exactly what I said. Maybe I'm just being somewhat opaque.
For me, it is very difficult to say about I'm thinking because
I appreciate that. Yeah, because you're expressing yourself in a non-native language. I appreciate that.
Thank you. Thank you.
Thank you. So the next question, Andrei.
There is Pressburger arithmetics, and it's infinite and decidable and complete. There is equivalence relation, and that one number is bigger than another. What the difference in your theory between Pressburger and Peano arithmetics?
Well, those are both axiomatic theories, right?
Yes.
Okay. I haven't talked about any axiomatic theories. I just talked about models. So you can collapse any model, and I was interested in collapsing the standard model. But of course, Peano arithmetic and Presburg arithmetic will have non-standard models. You can collapse those too. So I don't really think that what I've said has any application to any interesting application to Presburg arithmetic and Peano arithmetic.
There is no paradoxes in Presburger arithmetics, I think.
No, that's true. I mean, we hope it's consistent, right? We hope the Peano arithmetic is consistent. We hope the standard model is consistent. I mean, I agree with all those things.
Thank you very much. It was very interesting.
Thank you.
So, is there any other questions? Yes, you can just raise your hand or write in the chat. Well, I also have a question. So, in the collapse lemma, you show that if a closed formula is true or false in the original model, it remains true or false in the collapse model.
Correct.
But do you take the converse failure to be philosophically essential? In other words, is the point of the construction merely preservative, or do you want the new latitude truths of the collapse model to carry independent ontological significance?
Right. Certainly, if you collapse a consistent model, you're going to get an inconsistent model, right?
Mm-hmm.
So what I was assuming for the kind of finitism I was describing was that the collapse model actually tells you the way that mathematical reality is. Okay. Now, whatever you think are the ontological consequences of mathematics, then you're going to have to read those off from the collapse model.
Mm-hmm.
I mean, what do you think the ontological consequences of mathematics are is, of course, a hard question in
Right.
in the philosophy of mathematics. But whatever you think it is, you're going to have to say the same thing about the collapse model if you're this kind of finitist.
Mm, I agree. Well, thank you. Also, a question from my colleague from the chat. The finite collapse model appears to preserve arithmetical truths at the level of close first order sentences. And
Yep.
what happens to the explanatory role of induction? Does your finitist illusionist pictures preserve only the true values of sentences or also the structure that makes induction an eliminating principle rather than a brute regularity?
Um, I'm not sure that I understand what's meant here by explanatory purpose. I mean, every instance of induction is going to be true in the collapse model.
Mhm.
So but I'm not quite sure what to make of this notion of explanatory models. I mean, because we know that induction is true in non-standard classical models, right? So maybe can you tell me a bit more about what you have in mind by explanatory role of induction?
So it's a question from the chat. So if this man need to explain, I can wait a letter for him and then send you.
Okay, thank you.
Thank you. So with the any other questions? So if there is not, probably then we can finish. So Professor Priest, thank you very much for your talk and visit us on ride from New York to Russia. Thank you.
Thank you very much for inviting me. It's been a pleasure.
Yeah, it's been a pleasure for us too. So, can you please send your slides for our websites after
Sure.
the conferences?
Look, the talk is based on a longer paper, not that much longer, but would you prefer that I send you, do you want me to send you the slides and the paper?
Yeah, it would be nice. So we just put it in your paper and the slides, our website with the
Okay.
video link. I will send the link probably tomorrow after it will be downloaded.
Okay. So I'll send you both later today.
So that's all. Thank you again.
Thank you.
Have a nice day.
And the same to you guys.
Thank
So thank you all. See you next time. Bye.